I am back. If you missed my previous video, I was trying to build a model for a grappling hook with a rope. And I thought I did a pretty good job, but at the end I wasn't too happy with it. So the idea is, and I'll link to that video down below, I'm going to give you the short version of that. So if you throw a grappling hook up, as it rises, it pulls more rope with it, so it's going to be a more difficult problem to deal with. And so to me, I wanted to model that. You can see that. Let me zoom in here. Let me make this bigger. Let's see this, not this bigger. Right there. Okay. So here's my grappling hook, and each of these is these dots are my rope, right? And so the dots are masses connected by springs, and so the whole thing should work. And it kind of looks okay if you run it. It gets thrown up. There's my floor right there. I didn't draw the floor. But what bothers me is that this ends up so far in the X direction, in the negative X direction. A little bit would be okay, but not that much. Okay, so I'm not really sure what's going on. The first thing I'm going to do, let's just try playing around with the troubleshoot here. I have a graph. I'm not going to even change the axis of that graph, but instead of plotting the position versus time for the two analytical models, I'm going to just go ahead and plot the horizontal momentum of the grappling hook. Let's do that. I'm just thinking out loud. Because, yes, it starts off, the momentum starts off in the positive direction and the other masses are not moving. And the initial X momentum is 0. So this one can acquire some negative X momentum, but the other masses have to have some positive momentum in the X direction, because there's no net forces on it in the X direction, so the momentum shouldn't change in the X direction. So let's just plot the mass of the first one, and then we can look at something else after that. So down here, instead of plotting F1, I'm going to plot T, and the grappling hook is BS0. It's the first one on the list, .P.X. Let's just plot that and see what happens. I'm not going to plot this other thing because it has the wrong units. I'm not changing the axis of the scale or anything like that. Okay, so if I go down here, see it immediately jumps down to negative, but then it comes back up. I think I have to plot the total momentum. Let's do that. Let's calculate the total X momentum. This is off a little bit. Let's see this off. Let's put this right here. Let's put this right here. Okay. So I'm going to down here, at the beginning of each loop, I'm going to calculate the total momentum. So let's make a variable called, I'll just put this up here. Let's make a momentum called PT for total PTX, and it's 0. And then I'm going to go through and find the momentum of each one and each mass and add it to this. So down here at the bottom, I'll do this at the bottom. And remember, I'm doing this because this should be 0. Should be. For B in BS, PTX equals PTX plus B.P.X. So that's the X momentum of each one, adding it to the total, and then over here I'm going to plot BTX. PTX, PTX, X. Let's see what happens there. I'm trying to find what's causing the problem, or if there even is a problem. Okay, actually, I don't think there's a problem. Because, look at this. The X momentum is constant. Huh. So, if I let it run for a longer time, I think that, if I was able to plot the center mass, which I'm going to do next, if I was able to plot the center mass, if this piece keeps going that way, let's try this. Let's try decreasing the mass of the rope. If I decrease the mass of the rope, I can do that up here by just making this, that's the linear density. Okay. And you'll see, it looks like the center mass it looks like everything's right. It looks like I made a big fuss about nothing. Okay. But this is how you troubleshoot stuff anyway. Here we have still momentum's constant, so I'm pretty happy with that. Let's make the center of mass and plot that. The center of mass should be moving up because the initial momentum is up, but in the XY direction it should be constant. So I'm going to make an object called the center of mass, right here. COM, it's a sphere. Oh, I got to calculate it first. Okay. So RCOM is the center mass, is vector 0, 0, 0. So I'm going to add up the vector momentum of each, the RM, right, for each piece, and then divide by the total mass. 4B in BS. Go through each one, and then I can just say RCOM equals RCOM plus each mass B dot M times its position B dot POS. And so it'll give me a vector location of this of the center mass. And then I need to divide by the total mass, which should be, let's just do it. Let's just say MT is 0. I'm going to calculate it because I know I have a slight error possible there. So MT equals MT plus B dot M. And then the center mass, I have a vector location for that. COM is the center mass. It's a sphere. Its position is RCOM. Its radius is equal to, I want to see it. What was the radius of my grapple? L over 40. Let's make it a little bigger. L over 30. Let's make it color equals cyan. And then let's do make trail equals true. Okay. Now, down here, I just need to redo this stuff. Right? I need to every time I move my stuff, I need to recalculate the center mass. So I'm going to do that down here. Do it right here. Tab, 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 tab. And now I'm going to move my center mass. Center mass.pos equals RCOM divided by MT. RCOM is not the center mass. So actually I need to do this. RCOM equals RCOM divided by the mass. Then I can do this. And then up here I didn't do that either. Let's see. I'll just divide this by the mass. Okay. Let's see what happens. And again, what I'm thinking about is that center mass should not move horizontally. Okay. That's pretty good. Now let's make a heavier rope just for fun. I made it 10 times as small. Let's make it twice the density. So, okay, I made a big fuss about nothing. That's what I did. Let's make this 30 pieces, and let's make this at 0.05. Okay. All of that for nothing. Darn. Okay, let's go back down here and just double check something. I never plotted the stuff. So here's my FG. That's my plot for no gravity. And then I had a plot for this with gravity, which I called Y. And now I need to make one more graph up here. Let's call it F2 equals G curve. Color equals color.red. And then down here, I'm going to plot that F2.plot. I'm plotting the motion of the top. So BS0 is the top. .POS. .Y. Let's just see how they compare. Okay, and that's, see, I now know too. Okay. So these two, this is the no rope. And these two deviate because, I believe it's because of that rope pulling it to the left. Okay, so I think in the end, my original model was pretty good. But it's nice to check, right? And I'm pretty happy with this. So this is pretty good. It's kind of nice to see that I wasn't wrong. Okay, the end.